Hello, my name is Jared Keith Bettis, and I'm going to be presenting the aerodynamics of an insect. I would like to apologize ahead of time because I do not have a camera because my old laptop broke and my friend gave me this laptop, so I pardon myself for not having a camera for this duration. So let's get started. This is the table of contents. We're going to be going to the methodology used for this, the introduction, the motions of an insect, the results from the motions of an insect, the applications of studying the aerodynamics of insects, then the conclusion, references, and then finally we're going to go into some questions. Now, the methodology used for this is we're going to be using some key terms here. We're going to be using backstroke, forward stroke, stroke rate, stroke acceleration, normal force, angle of attack, and high B frequency. The type of sources that were used for this whole presentation was 5 journals from the last 5 years on the aerodynamics of insects from various sources. Now we're going to go into the introduction of the aerodynamics of an insect. So the studies about this certain topic have gone back to the 1980s. So this is not a fairly new topic that has been researched. This topic is important to physicists and engineers alike because of the applications that we're going to be discussing later on in this presentation. Now, the reason why this aerodynamics have been studied is because of the versatility they have been a recurrent source of inspiration for engineering devices. As I said earlier, this is engineering devices being used to mimic aircraft because of the wings of insects, because of the rigidity and flexibility. Like we says here, because of their wing flexes during flight, they provide a better understanding of structural mechanics and aeroelasticity mechanisms. So it helps us understand as humans how to better make aircraft that are more suitable for various conditions that will be explained later on. Now, we may be wondering what makes an insect fly. According to a journal, insects fly by moving their wings rapidly back and forth on a complex pattern. Now, in this study, we're going to be looking at various insects, and the first thing we're going to realize is to generate aerodynamic forces required for flight, two-winged insects, which is also the name Diptera, move their wings back and forth at high wing B frequencies. This results in exceptionally high stroke accelerations and consequently relatively high acceleration dependent fluid forces. Now, this two-winged insects can be a butterfly, it can also be a mosquito, it can be also a bee. They move at high B frequencies that allow them to fly, but it goes much deeper into that. The motions of an insect, what was found is in two-winged insects was the forward and backward stroke. As you can see to the left over here, we have a bee where it shows the forward stroke moving up and the backward stroke moving down. This is also very important. Now, during the forward stroke, the wing is moving from the dorsal side of the insect towards the ventral side. So I don't know if you can see, but in this image right here, the forward stroke, the wing is moving from the dorsal side, which is from its body, towards the ventral side, which is upwards. And then in the opposite side for the backward stroke. So in order for it to go backward stroke, you're moving up, it moves up, down towards the body. Now, stroke reversal is defined as the phase where the wing transitions from the forward stroke to the backward stroke and vice versa. So stroke reversal is just basically the phase that happens between the forward stroke and backward stroke that happens naturally. And when this happens during stroke reversal, the wing has to first decelerate and then accelerate rapidly in the opposite direction. This gives you the lift in insects, which allows them to also fly. Now, you may be wondering, scientists have wondered for a long time now is how do insects fly in turbulence flow? Well, this is important to know because in the last slide, we learned that there was a forward stroke and a backward stroke that enables insects to fly. Well, now the long answer that everyone has been wondering, how do insects combat turbulence flow? We see the concerns of aerodynamics of an insect, this turbulence environment has always been in question. Well, now we're going to be looking at the study of a bumblebee. It was found that in bumblebees that they change their wing kinematics, both static and dynamic. It was found that the bumblebee was found to bend their wings at various angles to stabilize themselves. So according to whatever environment they were in, they would also change their angle between 0 and 45 degrees. And depending on how they were moving their wings, depending on the environment they were in, they would bend it more or less, depending on what they were experiencing to be able to stabilize themselves and fly. Now, a cicada was also like documented, and the vortice map was displayed above. As you can see here, the wing's flexibility plays a factor in the insect's ability to fly and stabilize itself. The angle of attack, as discussed recently, can affect the way an insect responds to its environment. So as you can see here, as the local angle of attack was changing, you can see that the vorticity around its map was changing as well. Depending on what it was experiencing, the cicada was able to change its local angle attack almost immediately through CFD simulations. Now, let's see these results continue. There was a research paper that I found that they observed CFD simulations showing the normal force and the stroke acceleration acting on the wing itself. Now, as we said earlier, as the angle of attack changes, the stroke rate changes also. This can either cause an increase or decrease in stroke acceleration, depending on what the insect is going through and depending on where it's taken off from. It can either change its angle of attack, so its stroke rate can either increase or decrease. Helps it able to fly more and able to stabilize itself when in flight. Now, there's something to note here. The higher the normal force, the higher the stroke rate itself. As you can see right here on the left, the higher the normal force, along with the angle of deflection, you can see it either increase or decrease. When the angle of attack was at 9 degrees, which is what the wing was at 9 degrees from its backward stroke to its forward stroke, you can see that it was more constant. But as you keep increasing and increasing over here in angle of attack, say at 90 degrees, when the wing is literally perpendicular to the body, then we can see that the normal force is increasing more and more, and the stroke rate also increases. And you can also see that tangential forces show a constant linear relationship with the angle of attack, meaning the tangential forces acting on the wing. If it was acting on the wing at various angles, it did not dictate if there was an increase or decrease in the force itself. Now, you may be wondering, why are we doing this? What are the applications to studying insect flights? Well, what are the benefits of doing all this? Well, as said earlier, this topic brings interest to engineers and physicists alike. They bring to light ideas for engineering devices. Right here to the right was a drone that was invented by the Air Force. Now, you may be wondering, oh, this is just a normal dragonfly. In reality, it's not. It's actually a prototype made of a drone that was able to go into tiny spaces to do inspections of aircraft. The Air Force is hoping to do various applications with these insects, drones, and to further the aerospace industry. Another application was aircraft wings. They because of these wings, they help us make better designs. As you look at an insect wing, they are more rigid, they have more flexibility, and they can change depending on their environment conditions. Just like a wing, though, we can also change its rigidity and flexibility when it's going through turbulence flow in the air or either laminar flow by changing the panels itself or even the flaps of the wing. Conclusion. Insects that we found out have a forward and backward stroke they use to help fly. The shape and flexibility of an insect's wing plays a factor in how an insect flies. The veins and cross pattern of the wing itself plays a factor as well. The stroke rate, angle of attack, stroke acceleration map CFD simulation that helps stabilize an insect's flight path and helps us understand how insects actually fly. And because of this, studying the aerodynamics in insects have applications in the aerospace industry. These are the references that I use. Any questions?